Okay. Hi, everybody. We start this lecture on magnetism. The course of Introduction to Physics is not a comprehensive course of physics. It's rather a discussion of some selected topics of physics syllabus of the secondary school. And today's topic will be magnetic field. We start from the ancient times. Just a few words about what happened 1,000 years ago when people found some natural magnets in places where there is an iron ore deposit, and some pieces of iron ore can be found on the surface of the planet Earth. And people found such stones which were exhibiting magnetic properties. So thousands of years ago, people knew that there are magnets which interact with each other. And this interaction may be an attraction. Two magnets may be attracted to one another, or they may be repulsed if we turn one magnet by another side. So either interaction or repulsion, and people knew this property of natural magnets thousands of years ago. And about 1,000 years ago, about 1,000 years ago, in Chinese sources, ancient sources, it was written, the description was given of a compass. The compass, a simple device to determine the direction in space on the Earth's surface. This device contains a small magnetic needle which somehow always tends to show in one direction, from north to south, to the south. Such properties of magnets as interaction and alignment in space, if we suspend this magnetic needle by its center of gravity, then the magnetic needle, after some oscillations, will find its direction. And the direction is always the same, turns out to be the same from north to south. So this device allowed people to navigate and to know the direction to the north, even if the sky is closed with clouds and we can see no sun and no moon and no stars. We nevertheless know the direction from north to south, and due to this compass needle. Also, it was discovered later that something happens in the vicinity, in the space around a natural magnet. Magnets do interact with each other. It means that there is something in the space around the magnet, some distortion of space. And there is this distortion, and this something which is surrounding a magnet is called a magnetic field. And magnetic field may be visualized easily. It was discovered later that if you take a iron powder or iron filing, then you can visualize magnetic field if you place a piece of glass plate on the magnet and then spread iron powder on the glass plate and then tap on the glass plate so that the iron powder may be shifted a little bit. And then you notice that this iron powder or iron filings arrange along certain lines in space. And this arrangement can be shown like this. If you take a bar magnet, then after tapping on the glass which covers the bar magnet, the small pieces of iron powder will be arranged along certain lines. There are many, many such lines which can be depicted something like that. So this picture can easily be obtained for any piece of magnet if you have a glass plate and iron filings which will be aligned along these field lines. What happens in this case is well known today. Every small piece of iron powder will be magnetized in the external field of the bar magnet, and each grain of iron filing will have its own north and south pole, and other such grains will also have its own north and south poles if placed in the external magnetic field. And as unlike poles attract to each other, then these small grains of powder will be aligned along such a line in space that they will show the line of field, of magnetic field. They will be aligned along these field lines. So the field, the magnetic field of the bar magnet induce the magnetization in other iron pieces of iron. And therefore, because the magnetic field induces magnetization or causes the small iron particles to be magnetized, for this reason, this magnetic field, these magnetic lines are called induction lines. So this is a magnetic induction. And if you have a north pole of magnet and south pole, then the like poles will be repulsed and the unlike poles will be attracted. So this north pole will be attracted to this south pole, and this south pole will be attracted to this north pole. So unlike poles will be attracted and like poles will be repulsed. And because these small pieces of iron filing are magnetized and magnetism is induced in them, for this reason this field is called an induction. And usually it's denoted by letter B, which is certainly a vector quantity, and this is magnetic induction. Magnetic induction. All this was well known even even 5 or 4 or 5 centuries ago. And at first people knew little about magnetism, and they actually confused magnetism for electricity. Electric interaction was also known to people as electrostatic interaction, and magnetostatic interaction was also known, and people were not sure if this is the same phenomena or if these are two different phenomena. But before the beginning of the 19th century, people understood that these are two different phenomena, because if you cut the magnet, the bar magnet, into 2 separate parts, you will never obtain a separate south pole. You will obtain a smaller magnet which has its own south and north poles, and another piece of magnet which will have its own south and north poles. And if you cut this small magnet into even smaller parts, then you will again obtain a magnet which has 2 different poles, and you will never obtain a separate south pole and a separate north pole. Unlike in electricity, when electric charges can be obtained separately from one another, and electric charges, positive or negative charges, can be placed on different bodies and can be separated from one another. Magnetic poles cannot be separated from one another. That was the first indication that magnetic properties are different somehow differ from electric properties. And magnetic charges are not the same thing as electric charges, absolutely different. They have different properties. Then, in the beginning of the 19th century, some important experiments were set up, which allowed scientists to understand deeper what happened, what is the magnetic field. In 1820, Ørsted set up an experiment which showed that an electric field creates a magnetic field around it. If you have a straight wire with an electric current generates magnetic field around it. A constant direct electric current generates magnetic field, and the magnetic field can be discovered if you place a small needle, magnetized needle, a small magnet like a magnetized needle in the vicinity of this straight wire. Then the needle will always orient in some certain direction, and so if you place this needle in different points, you will discover that the magnetic field has some circular line, so that the needle always orients itself along this line. That was an experiment of Ørsted. Hans Christian Ørsted from Copenhagen carried out this experiment in 1820 and discovered that electric current creates magnetic field around this straight wire. So this magnetic field can certainly be visualized if you allow this straight. If you put a glass plate here nearby this wire with a current, and again spread some iron filings on this glass plate and tap on it, then the iron filings will show you these magnetic field lines, the lines of induction of magnetic field. Well, it's interesting that magnetic field lines are not have no beginning and no end. Magnetic field lines are closed. All the magnetic field lines are closed lines, and they have no beginning and no end. And unlike the electric field lines, in electricity, each electric field line starts on positive charge and ends on negative charge. So this is another difference between magnetic field and electric field. Electric field lines are not closed. They have a beginning and an end, while magnetic field lines are closed lines. They have no beginning and no end. In the same year of 1820, in the same year, a French physicist, Ampère, Charles Ampère, carried out an experiment which indicated that electric currents not only generate magnetic field around them, but also they interact magnetically with one another. If you take a straight wire with a current and another parallel straight wire with a current, and if these two currents flow in the same direction, then there will be an interaction between these two wires. They will be attracted to one another with some force, and this attraction was discovered by Ampère. But also, if you take two wires with different direction of currents, if currents flow in different directions, then these two wires will be repulsed from one another with some force. So the like currents are attracted, magnetically attracted, while unlikely directed currents are repulsed from one another. And this discovery of Ampère was very important as it showed that a current really creates a magnetic field which can not only be observed using the ion filings, but which can be detected by its force action on another current. Not only current creates the magnetic field around itself, but also another current placed in a magnetic field. Another magnetic field acts with some force on another current if it's placed in the magnetic field. There is some force of interaction. The first current creates magnetic field which attracts another current, influences or acts with some force on another current. And the second current also creates a magnetic field around itself, so that the second current acts with some attraction force on the first current. These two forces can be explained by magnetic interaction between currents. And this discovery of Ampere also led him to understand that if an electric wire with electric current is bent to make a current loop, and even several current loops, which is called a solenoid, then the current flowing here will create magnetic field. Magnetic field of such a structure, of a spring made of wire with a current. The magnetic field of such structure looks very much the same as the magnetic field of the bar magnet. So the magnetic field lines will be very much the same as if it were a bar magnet, as if it were the bar magnet. And this discovery led Ampere to a very important hypothesis. When he compared the magnetic field pattern of solenoid and the magnetic field pattern of a bar magnet, and when he discovered that these two magnetic field patterns, these two maps of magnetic field are actually the same, he came to a hypothesis that a magnetic field in a bar magnet and in any magnet is caused by some currents, by some electric currents which flow inside the magnet. And Ampere introduced such a hypothesis that each atom or each molecule each molecule of which the magnetic substance is made, each molecule carries some internal current. There is an internal current in each atom or each molecule. And so that two molecules have such currents, and three molecules will have such currents, and so on. If you have many molecules in a solid body, each molecule will have a small current inside it, small circular current. Well, it was surprising because this current must flow constantly. It will not decay with time. It will not diminish. The current strength will be constant in time, and which means that there is no resistance inside atoms and molecules, no resistance to the motion of electrons. Ampere knew nothing about electrons and knew very little about atoms and molecules, but he made such a hypothesis that inside a magnetized body, electric currents flow inside each molecule. And look here, this current goes in one direction and the current of a nearby molecule goes in opposite direction. And the same here, the current here goes in this direction and the current in nearby molecule goes in opposite direction. So inside the body, all the currents cancel each other, and only on the surface of the body there is a non-cancelled current consisting of currents of nearby molecules which are on the surface of the body. So there is a circular current on the surface of the body, and this current flows inside the magnetized magnetic bar So there is internal current inside which creates the magnetic field of the magnet in the same way as the electric current in the solenoid creates similar magnetic field. That was a hypothesis introduced by Ampere, and these currents are called Ampere currents, and further development of physics fully confirmed this hypothesis, and it turned out that actually magnetism can be attributed to an internal electric currents which flow inside atoms and molecules. When people carried out experiments with magnetic fields, an important question, there was an important problem: how to measure the strength of magnetic field, how to measure the magnetic inductance. Well, it turned out that magnetic field is acting on currents, and Ampere was the first one to discover. Что там случилось?
Проблема с камерой, просто штука ненадежно стоит, из-за этого оно периодически пропадает картинка отсюда.
А здесь написано слабый сигнал или нет сигнала. Это имеет какое-то отношение к делу?
Вот. Отлично появилось.
Okay. Is it okay? Okay, good. So if currents interact with each other and currents interact with magnetic field, then what happens if we take an electric current loop, that is the wire which is bent in such a way as to form a loop so that the current goes in this direction and then the current flows here and here. How will this loop interact with external magnetic field? So imagine that the magnetic field is directed, magnetic field line or magnetic field induction is directed along the surface of this blackboard. So the magnetic field direction is something like this. What happens? This experiment can easily be carried out because to create a magnetic field which is uniform in space, we just need to take a solenoid, and inside the solenoid the magnetic field turns out to be uniform if the solenoid winding is uniform. So if the solenoid is created uniformly with the constant number of turns per centimeter, then the magnetic field inside the solenoid turns out to be uniform. And if we put in this uniform field a small electric current loop, then, as an experiment shows, the loop will turn in such a way, if it can easily rotate about this axis, then the loop will turn in such a way as to orient its area perpendicularly to the magnetic field line. And if the magnetic field lies in the plane of this electric current loop, then there is a torque acting on the loop, a torque which tends to rotate it. And the torque, I will denote it with a capital M. The torque depends on the angle of rotation, and the maximum value of this torque is measured when the normal to the surface of the electric loop, normal to this electric loop area, is perpendicular. The perpendicular to this surface is perpendicular to the magnetic field line. That is, when the magnetic field line is in the surface of this, in the plane of this electric loop, in this current loop, then the torque acting on the current loop is maximum. And maximum torque turns out to be proportional to the electric current flowing here, and also proportional to the area of this electric loop, which I denote by S. And also it's proportional to the magnetic field strength. And we can measure this torque, because torque is just a pair of forces acting on the electric loop made up of wire. And we can measure this torque by measuring the small angle of rotation on an elastic axis. And we can certainly measure the area of the loop, because we do this loop with our own hands. We can easily measure the area, and we can measure the current in this loop. And so using this formula, using this experimentally obtained formula, we can measure the intensity of magnetic field, because this is a mechanical quantity, a torque, a mechanical quantity which can easily be measured. And these quantities are also known from the experiment. This can also be measured. So from this formula, it turns out that magnetic field equals IS equals the maximum torque acting on an electric loop divided by IS, by current times area of the current loop. This quantity, current times area, is called a magnetic moment of the electric current loop. So the magnetic field can be measured as the maximum torque acting on the current loop divided by the magnetic moment of the current loop. All these quantities can be measured in the experiment, and so the magnetic field can be measured at any point where we place this small electric current loop and measure the torque acting on this loop, the maximum torque acting on this loop. And I repeat, the maximum value for this quantity is attained when the loop area, or the surface of this loop, belongs to this magnetic field. Magnetic field is parallel to this area. Then the torque acting will be maximum. And when the magnetic field is perpendicular to the surface of the loop, then the mechanical torque acting on the loop will be zero, will be minimum, will take its minimum value if the magnetic field is perpendicular to the loop. So all this experimental data, all these results allow one to measure the intensity or induction of magnetic field. At this point, it's the right place to say what are the units of measurement of magnetic field. From this formula, we can derive that the magnetic field in the international system of measurements should be measured in what? The torque is the force, which is force measured in newtons times meter, the arm of the torque, the arm of the force. And here we have ampere to measure the electric current, and the area, which is measured in meters squared. So the magnetic field will have units of measurement in the international system will be measured in Newton divided by ampere times meter. This unit, Newton divided by ampere and meter, is called Tesla and is denoted by capital T. This is Tesla. And so magnetic field in such a procedure is measured in Tesla. Tesla is very large magnetic field. its magnetic field of 1, 2, 3, 5 Tesla can be created in laboratory, but if you want to create 20 Tesla or 50 Tesla, that's a problem. That's very high, very strong magnetic field. By the way, magnetic field of the Earth is 10,000 times smaller, about 10,000 times smaller than 1 Tesla. But actually the magnetic field of the Earth is different in different places on the planet. Magnetic field of our planet is the strongest near the pole, near the North Pole and near the South Pole, and magnetic field is much smaller near the equator of the Earth. So magnetic field of the Earth is different in different places. By the order of magnitude, magnetic field of our planet is 10,000 times smaller than 1 Tesla. So 1 Tesla is a strong magnetic field. As far as the magnetic field of the solenoid is concerned, experiments show that the magnetic field of solenoid inside the solenoid, where the magnetic field is uniform, is proportional to the current which flows here, and also is proportional to the number of turns per unit length of this solenoid. So if we have total number of turns N and the total length of solenoid L, that is the length from here to here, the total length of solenoid, then the number of turns per unit length will be total number of turns divided by total length of the solenoid. And as the magnetic field, magnetic induction of the uniform magnetic field inside the solenoid is proportional to this quantity, then we introduce a coefficient of proportionality to allow for this relationship to be not merely a relationship of proportionality, but a strict equality. We introduce a coefficient of proportionality, which is denoted by a mu0, and then we have current times small n, the number of turns of the wire in solenoid per unit length of the solenoid. And this coefficient of proportionality is called a magnetic constant. Sometimes people call it a magnetic permeability of vacuum, but it's more usual to say that this is a magnetic constant, and it's equal in the international system 4 pi 10 to the minus, and it has its own units of measurement, and the units will be Tesla, which is the unit of magnetic field, divided by ampere. And n is the number per unit length, and unit length is a meter. So number of turns per meter, and meter will come here in the nominator. So this is units of measurement of magnetic constant. On this point, I would like to solve a simple problem. Let's discuss how to calculate magnetic fields in solenoid. Suppose we have a solenoid of length 20 centimeters. That's not very large, not very small, medium length of 20 centimeters. And the number of turns of wire in this solenoid is 500 times 500 windings of wire. And the current in the solenoid is 0.1 ampere. And what will be the magnetic induction inside the solenoid where the magnetic field is uniform? So by using this formula, we immediately obtain the answer. That will be mu 0. You can also say mu naught or mu 0. Both ways are possible. And electric current and the number of turns per unit length of the solenoid. And mu 0 is 4 pi 10 to the minus 7 in international system. And the current is given is 0.1 ampere. And the number of turns can easily be calculated. That is 500 divided by 20. But centimeters is not meters. We have to use meters in the international system. So we have to convert centimeters into meters. And if we do this, we obtain 0.2 meters. So we have to divide by 0.2 to obtain the answer. And so upon doing it, 0.1 divided by 0.2 will equal 2 in denominator, and 500 divided by 2 will give you 450 times 4 pi 10 to the minus 7, and 450 times 4 will give you 1000. That is 10 to the power of 3 and 10 to the power of minus 7 combined with this 1000 will give you, the pi remains here, will give you 10 to the power of minus 4. And that will be, well, about 3.14 Tesla, because we're calculating the magnetic field induction, which is measured in Tesla in international system. And that will be, if we use we use more convenient unit like millitesla. Millitesla is more convenient in practical life. Then that will be 0.314 millitesla. That's the magnetic field induction inside. That will be a magnetic field induction inside such a solenoid. Well, another thing which is important to mention, you should understand that if an electric current creates a magnetic field, then each small charged particle, each electron which moves here, should also create a magnetic field, because the current is the directed motion of charges, and if we have motion of some electrical charges here with some velocity, then each electrical charge, each charged particle moving here must create its own magnetic field, and so and it will be of the same pattern practically. So if we have a charged particle which bears charge q, we'll say plus q, and this charged particle moves with some velocity, then this is an element of electric current. And like a small element of electric current, such a charged particle moving with velocity v must create a magnetic field of the same pattern around it, the magnetic field of the same pattern. So, and the pattern is that circular concentric lines of magnetic induction lines, concentric lines which are circular and have the center at the electric current wire. So each electric charge, which is a part of electric current, creates a magnetic field when it's moving with some velocity v. And how to determine the direction of this magnetic field? In order to determine the direction of magnetic field, it's easy to use the rule of a screw, the right screw. If you take a screw and move it in the direction of the current, then the screw will rotate, and the direction of rotation will show you the direction of magnetic field induction lines. So if you screw in the direction of the current, then the direction of screw rotation will show you the direction of magnetic field. And the direction of the current is accepted to be the direction of motion of positive charges. So if a positive charge moves here and you move in this direction, the screw, then it will show you the direction of magnetic field. If a negative charge moves in the same direction, then the direction of the current will be opposite, and the magnetic line will have opposite direction, like this one. Magnetic induction created by a moving current, a moving charge, will have this different direction. Another important thing is the interaction of a current with magnetic field. So we have already discussed this experiment by Ampere when two currents interact magnetically. It means that one current is placed into a magnetic field created by another current. But the magnetic field may be created by a solenoid, for example, or by a natural magnet, by bar magnet, etc. So we should consider such a situation when a magnetic field is created externally, and in this external magnetic field we place a current, and as there is an interaction between the current and magnetic field, we have to know a formula which describes this interaction. So suppose we have a current flowing in the straight wire and a magnetic field which is perpendicular to the blackboard. Magnetic field vector will look from the blackboard to you. So this situation is usually indicated in the picture by such a symbol. That means that the arrow of the magnetic field vector is directed to you, towards you. And in this case, there will be an interaction between this current and the magnetic field vector. And how to find the force of interaction? First of all, the direction of this force. If we want to find the direction of magnetic field, we use the rule of the right screw. But if we want to find the direction of the force acting on the current, we have to use the rule of the left hand rule. We place the left hand in such a way that the four fingers of the palm are directed along the current, and the palm is oriented in such a way that the magnetic field goes into the palm. So in this case, I should place it this way, and then this finger, this thumb will show the direction of the force acting on the current from the magnetic field. And this force turns out to be proportional to the electric current and proportional to magnetic field. The larger the current, the larger will be the force in the same magnetic field, and the larger the magnetic field, the larger will be the force in the same current, for the same current. And also the force is proportional to the length of this wire with current. So I may take some length L, and the the force actually is applied to each small element of the current, and the larger the length of the wire is taken, the larger will be the force acting on this section of the wire with the current. So the force will be proportional to this expression if, and that will be the exact equality if and only if the direction of the current is perpendicular to the direction of magnetic induction. If they are perpendicular, then this will be a strict equality. If there is some angle between the current and the field induction, then you will have to use some geometrical function here, that is sine phi, where phi is the angle between the electric field and the magnetic induction vector. So that if the magnetic field is directed along the current, then the angle between the magnetic field and the current will be 0, and the sign of this vector, the sign of this angle will also be 0, and then the force of interaction will be 0. So magnetic field does not act with any forces if the magnetic field has the same direction as the current. And then the force will appear if this angle phi is other than 0, and the maximum magnetic field will be observed when the magnetic field is perpendicular to the current. That is in the case when sine phi is sine of 90 degrees, which is unity. So in this case, the magnetic field will be defined by this formula, which is the maximum of possible force of interaction between the magnetic field and the current. But what is current? What is current? Electric current, by definition, is some electric charge which flows through the electric conducting wire, through some cross-section of this wire within a unit time. So I can put it like this. Electric current is some charge which flows through the wire during some time t. So if I put it here or here, I would like to put it here. The electric current is the electric charge that goes here through the cross section of the wire by some time interval during which this charge flows, and times I would put it like L and B. So if we take the time exactly the time which is needed for the charge to go this length L, then the length L, or the displacement of the point charge, divided by t will be the velocity of the charge motion. So we will have the charge times its velocity times magnetic induction. And that will be the force acting on the charge which is here, which is moving here on this section of the wire. The charge which is located here on the wire and moves and makes the electric current. And this is the formula for the force acting on the electric charge if it has some velocity and the charge moves in the magnetic field. This formula is called, by the way, the Lorentz force. Lorentz force. This is the Lorentz force, and this formula should be used to calculate a force acting on charge q if it moves with velocity v in the magnetic field, which is described by induction B. Certainly this formula is correct only in case the velocity of the charge is perpendicular to the induction of magnetic field. If the velocity is perpendicular, then we use this formula. If the velocity of the charge is not perpendicular, somehow we move the charge at some arbitrary direction, then we'll have to use another sign phi here, another sign of the angle between the velocity and the magnetic field. This may happen if the charge is displaced by some external actor, by some external force, which is not only the force from the magnetic field is acting on the charge, but some other forces apart from the forces from the magnetic field. Then there may be some angle between the velocity and the magnetic field. However, if the charge moves freely in the magnetic field and only the magnetic field is acting on the charge, then the magnetic field will always act with the force perpendicular to the velocity. So if we have a charge q moving in this direction and the magnetic field is directed here, then the force acting on the charge will be perpendicular to the velocity of magnetic field, and this force will cause only the deflection of the charge trajectory, so that the charge trajectory will be like circular trajectory with some radius of curvature, and the magnetic field will not produce any work and will not change the velocity of the charge. If the charge flies freely in free space, in vacuum, and only the magnetic field is acting on this charge. But sometimes it happens that charges move not only due to magnetic field force, but also due to some external forces, which is the case in any electric generator. Now, as we know the force with which the magnetic field acts on a current, we can calculate the force of interaction between two currents. The force of interaction between two currents. But in order to derive this formula, we have to use another formula which describes the magnetic field of a straight current. In this case, the magnetic field induction depends, at this point, depends on the distance r between this point of observation and the straight electric current. And the magnetic field is proportional to the current strength and inversely proportional to the distance between between the point of observation where we want to measure the magnetic field's induction and the straight electric current. So this is the distance between these two quantities. And this is just proportionality which can be established experimentally. Experimentally, we can change the strength of the current and measure the magnetic field here, and it will turn out that the magnetic field induction, which can be measured, as I have shown you, using the small loop with current, for example, then we will discover that the magnetic field induction will be proportional to the current and inversely proportional to the distance. Closer to the current, the magnetic field induction will be larger, and if we go farther from the current wire, farther from this straight wire, then the magnetic field induction will become smaller and smaller according to this formula. But if we want to calculate it exactly, then the formula will look something like this: 4 pi magnetic constant electric current 2 pi r. So this is the magnetic induction of magnetic field created by an electric current. magnetic induction depends on the distance from the electric current, inversely proportional. And now, as we know, the force of interaction between the electric current and the external magnetic field, and as we know what magnetic field is created by another current, then we may calculate the force of interaction between two currents. I will put it here, the force of interaction between two currents. So the force should be directly proportional to the current, and let us denote this current as I1 and I2, maybe two different currents. So the force acting on the second current will be directly proportional to the strength of this second current, and also directly proportional to the magnetic field created by the first current and the length of wire of the second current. And as we can calculate the magnetic field created by the first current by this formula, we can substitute this expression into our expression. We can substitute this expression for the magnetic field, and then we can write down that this will be I2L, and the magnetic field will be mu0 electric current, which creates this magnetic field. This is the first electric current divided by 2 pi r. R is the distance between the two straight wires in this case. And that will give us the following expression. That will give us the mu 0 divided by 2 pi, and then first electric current, second electric current, the length of the wire divided by r. That will be the force, the formula describing the force of interaction between two electric currents. Two electric currents enter symmetrically into this formula, which means that the force acted on the second current equals the force acted on the first current, in accordance with the third Newton's law. And also the force is proportional to the length of the wire. If we take a small section of the wire, then the force acting on this small section will be rather small. But if we take a longer section of the wire, then the force will be proportional to the length of the wire on which we measure the force acting on it. And the force will be inversely proportional to the distance between the two wires. And such is the formula for the interaction between the two currents in Ampere's experiment. Ampere interaction of currents, electric currents. Another thing which I wanted to mention today is the influence of a magnetic medium, a magnetic substance. If we put some magnetic substance here, for example, if we put a magnetic core inside a solenoid, a steel core inside the solenoid, then this steel core will amplify the magnetic field. The resulting magnetic field will turn out to be many times stronger, and that phenomenon is taken into account in this formula, for example, by another coefficient which describes the influence of a magnetic material, magnetic core inside the solenoid. So that the magnetic field, uniform magnetic field inside the solenoid, will be given by the same formula, but the magnetic field will be much stronger. It will be much larger if we insert a steel core or iron core inside the solenoid. And therefore, as the magnetic field will be much larger, we introduce another coefficient which is larger than unity, and then the same quantities as the electric current in the solenoid wire and the number of solenoid wire turns per unit length of solenoid. And this new coefficient is called magnetic permeability. Magnetic permeability of a solenoid. For different iron alloys, which include probably nickel or cobalt, this quantity may be very large. It may increase the magnetic field considerably, and so this may be much larger than unity for ferromagnetic materials. And there are also not everything is ferromagnetic. Many materials do not influence much the magnetic field, and some materials do even reduce the external magnetic field. So if this quantity mu, magnetic permeability, is less than unity, then such a substance will reduce the magnetic field, and such a substance is called diamagnetic. Diamagnetic substance. And if mu is slightly larger than unity, it will increase the magnetic field, but not considerably, just increase by a few percent probably. That will be a paramagnetic substance. Paramagnetic. And if this mu, magnetic permeability, is much larger than unity, then this will be a ferromagnetic substance. Ferromagnetic. In that way, we take into account the magnetic properties of a substance which is placed in external magnetic field. Different materials influence the magnetic field, external magnetic field, in different ways. Some materials, like diamagnetics, may slightly reduce the external magnetic field. Other materials, which are called paramagnetic, may slightly increase the magnetic field, and other materials, which are called ferromagnetics, may considerably increase the magnetic field, many times and many hundreds of times. This magnetic permeability of the substance takes into account the magnetic properties of a material, of substance. Sometimes, in order to calculate magnetic fields, it's not easy to take into account the geometry of magnetic substances. The geometry may be very complicated. For example, you have some arbitrary magnetic field created by some currents. So you have a current loop here with current I, and you have a straight current here, and there will be an arbitrary magnetic field of complicated structure, and also there may be a magnetic substance here, a magnetic substance of arbitrary shape, so that this magnetic substance with some magnetic permeability will certainly influence the magnetic fields created by the currents. And to solve such a complicated problem, well, it's a difficult problem. And in order to solve it, people introduced such a method that first, consisting in this simple idea, first we calculate magnetic fields only based on the currents, with not taking into account magnetic properties of substances. And if the magnetic field is calculated based on the currents, then we use before this procedure, we use such a notation that magnetic field, real magnetic field induction, is mu0 mu, and this is a magnetic field strength, which we calculate not taking into account magnetic properties of substances. So first we calculate magnetic field strength, which is determined by external currents, like in solenoid like in this simple situation with solenoid. We calculate the magnetic field strength. This is not a real magnetic field. This is just a mathematical trick. This is just a field which simplifies the solution of problems. This field can be calculated based on the currents, and it does not take into account magnetic properties of matter, and also it doesn't take into account magnetic constant μ0. So this is some fictitious magnetic field which is introduced only to simplify the solution of complicated mathematical problems when we have magnetic fields in the presence of magnetic substances, so which can be magnetized by external fields. So after we have calculated this magnetic strength, magnetic field strength, we can, knowing the structure of this magnetic field, we can calculate the real magnetic field vector, which is μ0 h, taking into account the influence of magnetic substances. So the only thing I want to tell you, if you encounter a magnetic field strength h, don't be afraid. This is also something like the magnetic field, something in simple situations this h is proportional to magnetic field, and the coefficient of proportionality can be taken into account later. So on this point I would like to consider some problems in magnetism, and first it will be problem number 546. Problem number 546. It says that a current I flows through an infinitely long conductor bent to form a right angle. So we have an infinitely long wire, conducting wire, which is bent at right angle here. And it's denoted as A, B, C. And the current here is I. And we observe the magnetic field created in this point, which is the which belongs to the line BC and point M. So a current I flows through an infinitely long conductor ABC bent to form a right angle here, 90 degrees. And we observe the magnetic field in this point. And the question is, how many times will the intensity of the magnetic field change at point M if an infinitely long straight conductor BD, is attached to this point, is connected here. So we bring in another straight wire and connect it at point B to the initial wire which was bent at right angle in point B. So, so that the current at point B branches into two equal parts. So after we connected another wire here, the current is branching in equal parts, so that we have, originally here was current I, but now we have current I over 2 here and current I over 2 here. At point B, the current will branch in equal parts and flow. Half of the current will go here and half of the current will go here. So how many times will the intensity of the magnetic field at this point change after we attach here, connect another wire, if the current branches and divides by half? if the current branches at point B into two equal parts, and the current in the conductor AB remains the same. Such is the problem. So originally we had some magnetic field B, say 0, and it was proportional to the current I. And I remind you that initially we have no second wire, no second conductor, only the first wire which is bent at the right angle, and nothing like this. So initially the magnetic field here is proportional to current I, and there is some coefficient of proportionality. I'm not much interested in this coefficient. The only thing I need to know is that the magnetic field is proportional to current flowing in this wire, because this current creates a magnetic field around it in such a way that the magnetic field will be circular, will have concentric circular magnetic induction lines. And so some magnetic induction line will go through this point, and it will be directed, as we can use the right screw. If it goes in this direction with the current, then the magnetic field will look here from the blackboard to this hole. So there will be some magnetic field proportional to this current flowing in this wire. And the current flowing in this wire will not influence the magnetic field here, because it's on the line with this current. It will not influence, because this current creates magnetic field which is directed, which has this direction, and it, according to the symmetry conditions, if this point belongs to this line BC, then the current flowing through this wire BC will not influence the magnetic field here due to symmetry considerations. And then that was the initial magnetic field. And then we attached a new wire here, we connected it so that the current now branches, and only half of the current goes into the wire BD. And now we have different magnetic field at point M, because the situation is different. The configuration of currents has changed. The current here at this wire does not change. So this magnetic field will certainly be present. It will not change, because the current here remains the same in this section of the wire. This will create the magnetic field as it was in the original configuration. But then similar magnetic field will be added due to the current flowing in this wire BD. And this magnetic field will be also proportional to this current, but current here is only I divided by 2. And the coefficient of proportionality will be the same. So the magnetic field after the new wire was connected here, the magnetic field in point M will be given by such a formula. We know that the magnetic field will be proportional to the current flowing in the initial wire and will be proportional to the current flowing in the new wire, but the current in the new wire is just half of the initial current, and the coefficient of proportionality is the same. So now we can easily find the relationship between these two magnetic fields, because the problem asks how many times will the magnetic field change, and how many times, what will be the change in magnetic field. So in order to determine how many times was it changed, we may divide B1 by B0, and by dividing it, we can easily arrive at final solution. By dividing, K will cancel and I will cancel, and what remains here will be just 1 plus 1 over 2 divided by 1. That will be 3 over 2. So that's the relationship between the initial magnetic field and the final magnetic field, which will be measured at point M after we have connected the new wire here. That's the final answer to this problem. Another problem I would like to consider. Another problem. Let's do it here. I would like to consider problem number 559. A rectangular circuit ABCD, I will put it here, a rectangular circuit ABCD. So this is a rectangular wire which has sides A. A is the length of vertical side, and B is the length of horizontal side of this wire, of this current loop. This loop made of conducting wire is placed in a homogeneous magnetic field with an intensity H, or it's better to say with inductance induction B. So we have a uniform magnetic field here, a uniform magnetic field in all this space. In all this space, uniform magnetic field B, which is perpendicular to the plane of this loop of wire, loop made of conducting wire. And this loop may rotate about this axis. Axis, say, let it be O prime. So the loop may rotate about this axis, vertical axis. A direct current is constantly flowing through the circuit. So there is a direct current which flows through this conducting loop. So we have a current loop, which is placed in uniform magnetic field, and the geometrical dimensions are known. A and B are the sides of this current loop. Determine the work performed by the magnetic field when this current loop is turned through 180 degrees if initially the plane of the circuit, the plane of this loop, is perpendicular to the magnetic field and arranged as shown in the figure. So initially the plane of this current loop is perpendicular to the magnetic field. Magnetic field is perpendicular to the plane of this picture. And it's known that the loop, sorry, something happened with this sound device, okay. The loop has turned by 180 degrees, so that this side turned and occupied the place of the opposite side, and the opposite side turned and occupied the place of this side. So these two sides changed places because the loop turned in the magnetic field by 180 degrees in this way. And we have to calculate the work. Done by the magnetic field in this situation. Why do we have some work A? Because the magnetic field is acting on the wire with the electric current with some force. And this wire is displaced in the magnetic field. And the displacement, well, say some delta x. And so some work delta A will be performed because the magnetic field is acting on this side with the wire, but also the magnetic field will act on another side. And what will be the forces acting on this on these two wires? So in order to find the force, we have to use the left-hand rule. We have to direct the four fingers of the left-hand palm along the current and direct the palm in such a way that the magnetic field vector enters the palm, and then the direction of the thumb will show the force acting on this conductor. So the force will act here, and on this conductor the force will be opposite because the magnetic field has the same direction while the current has opposite direction. So there will be forces acting on both sides of the loop, and when the loop is turned, the forces will perform some work. So if F is the force acting on one side and delta A is the work performed by this single force acting on one side, then similar work will be performed by the forces acting on the other side. And so the total work will be twice the work of the force acting on one side because we have two sides. And then now we have to take into account what is the force acting on the current. So coefficient 2 remains on its place, and the force is proportional to the electric current and the length of this side on which the force is acting, and the length is given, it's A, and the magnetic field induction B. And also we have to take into account the displacement of this, wire which carries the current. So the force is acting in this direction, and the displacement is in circular direction because the loop is just rotating. So this wire goes along circular trajectory. But if we displace this wire perpendicularly to the force, then the perpendicular displacement will cause no work. No work will be performed on perpendicular displacement of the wire, because the work equals the force times displacement times the cosine of angle between the force and displacement. And if the displacement is perpendicular to the force, then the work is produced is zero. So we don't have to take perpendicular displacement. Perpendicular displacement perpendicular to the force performs no work at all. And we have to take into account only the displacement in the direction of the force. So the displacement in the direction when this wire goes to the place of the second wire, the displacement in the direction of the force will be equal to B. So delta x equals B. That's the only displacement we have to take into account, because displacement perpendicular to the force does not make any input in the work performed. So the displacement here will be small b. And after that we obtain that small a times small b will be the area of this loop, which I denote by S. The area is AB. And so we will obtain 2 times electric current times the area of the loop times the induction of magnetic field. By the way, current times area is the magnetic moment of the current loop by definition. So we may put it as 2 magnetic moment of the current loop by the magnetic field induction. So this will be the work performed by the magnetic field if we turn the current loop, a loop with electric current, by 180 degrees. That will be the answer Yes, the question was, determine the work performed by the magnetic field when the current loop is turned through 180 degrees if initially the plane of the loop was perpendicular to the magnetic field. That's it. Okay, that's correct. That's correct. Twice the product of the magnetic moment of the current loop times magnetic induction of the external field. Well, I think we have no more time. That's the end of this lecture. And the next time we will continue discussion of magnetic fields. We have not yet discussed a very important property of magnetic field, which is Faraday's law of magnetic induction. And we will solve more interesting problems next time. Thank you and goodbye.